Introduction. Today, our physics teacher is going to perform an experiment in the physics lab. She starts the experiment in front of the students. She took a cardboard having a hole at the center. She made an electronic circuit and passed the wire from that hole. Then, she sprinkles the iron dust on the cardboard uniformly. After set up the arrangement, she switches on the circuit. When she switches on, some movement is shown in the iron dust particles and they start arranging in concentric circles pattern. She performed this experiment to show you the magnetic effect of current. You saw the iron dust particles arranged into the concentric circle pattern due to the magnetic field generated by the electric current. Students, today we'll study more about the moving charges and magnetism. Objectives. At the end of this lesson, you will be able to explain Oersted's experiment, define Lorentz force, define Fleming's left hand and Maxwell's corkscrew rule, calculate magnetic force on a current-carrying conductor, explain motion in combined electric and magnetic fields, describe cyclotron, define Biot-Savart law, calculate magnetic field on the axis of a circular current loop. Oersted's experiment. Oersted observed that a straight wire carrying electric current deflected a nearby magnetic compass needle. When the wire is held above the needle and the current flows from south to north, the north pole of the magnetic needle gets deflected towards the west. And when the wire is placed below the needle, the direction of deflection of the needle is reversed. The alignment of the needle is tangential to a circle centered on the wire. The deflection is stronger on increasing the current or bringing the needle closer to the wire. Iron filings sprinkled around the wire arrange themselves in circles concentric to the wire. Aurora borealis. It is a natural phenomenon displayed as magnificent colors in the sky in the latitudes near the poles. Electrons and protons mostly emitted by the sun during a solar flare are trapped in helical paths along the Earth's magnetic field. These particles become crowded near the polar regions where the Earth's magnetic field lines are closer. They occasionally collide with atoms and molecules in the upper atmosphere, causing them to emit light. In the north, this phenomenon is called the aurora borealis, and in the south, it is called the aurora australis. Lorentz force. A charge Q moving with a velocity v in a magnetic field B experiences a force generally known as the magnetic Lorentz force. It is given by F is equal to Q into cross product of V and B. In magnitude, F is equal to QVB sin theta. The magnetic force on a charged particle moving in a magnetic field has its maximum value when the particle moves perpendicular to the magnetic field. F max is equal to QVB. Minimum value when the particle moves in the direction of the magnetic field or opposite the field. F minimum is equal to 0. Fleming's left-hand rule. If the forefinger, central finger and thumb of left hand are stretched mutually perpendicular to each other, such that the forefinger may point field and central finger may point current, the thumb will show the direction of force. This rule is used for a current-carrying wire in a magnetic field, such as a wire on the armature of a motor. Maxwell's corkscrew rule. Imagine a right-handed corkscrew placed along the current-carrying conductor. If the screw is rotated so that it moves in the direction of flow of current, then the direction of rotation of the thumb gives the direction of magnetic lines of force. Magnetic force on a current-carrying conductor. The moving charge carriers constituting a current in a conductor experience magnetic force when the conductor is placed in a magnetic field. We consider a segment of a conductor of uniform cross-sectional area A carrying a current I in a uniform magnetic field B. We consider a current element I dl of the conductor. The number of free electrons in the element dl of the conductor is NaDl, where N is the number density of free electrons in the conductor. The magnetic force experienced by the current element IdL is given by minus ENaDl into cross product of V and B, which is equal to I into cross product of dl and B, where I is the current in the conductor. The resultant force F on the conductor is the vector sum of the contributions of all the elements constituting the conductor. Now we get the result F is equal to I into cross product of L and B. The magnitude of magnetic force on the straight conductor is given by F is equal to BIL sin theta. Example. Let's take an example of magnetic force on a current-carrying conductor. A horizontal wire 0.1 meters long carries a current of 6 ampere. What magnitude and direction of magnetic field can support the weight of this wire, where mass is 3 into 10 raised to the power minus 3 kilogram? Let's see the solution. Here, the given values are L is equal to 0.1 meters, I is equal to 6 amperes, M is equal to 3 into 10 raised to the power minus 3 kilogram. Force due to magnetic field on current-carrying wire when the field is normal to the straight conductor is equal to BIL. Weight of wire is given by mg. On comparing these two equations, we get BIL is equal to mg, which can be written as B is equal to mg divided by IL. By putting the values and calculating, we get the value of B is equal to 0.49 Tesla. Hence, magnetic field of 0.49 Tesla can support the weight of the wire. Circular motion in a magnetic field. We consider a charge Q traveling in a uniform magnetic field B with a velocity v perpendicular to B. As the magnetic force always acts perpendicular to V, the velocity of the charge changes only in direction, but the speed v remains constant inside the field. The force having a constant magnitude and its direction is always at right angles to V gives rise to a uniform circular motion of the charge. The centripetal force required by the charge to describe a circular path is provided by the magnetic force. The radius of the circular orbit is given by mv divided by qb. helical motion in a magnetic field. We consider the initial velocity v of the particle that makes an arbitrary angle with the field B. The velocity component parallel to the field remains constant, while the component perpendicular to the field results in a circular orbit. Radius of the helix is defined as the radius of the circular component of the orbit. Radius of helix is given by perpendicular component of velocity divided by frequency, which is equal to m into perpendicular component of velocity divided by qb. Motion in combined electric and magnetic fields. Velocity selector. If a charge with velocity enters a region where both electric field and magnetic field exist in such a way that the electric force and magnetic force are equal and opposite, then the charge will move undeflected in the fields. This can happen with velocity, electric field and magnetic field are mutually perpendicular to one another. Cyclotron. The cyclotron is a machine used for accelerating charged particles such as protons or ions to higher energies. Principle and working of cyclotron. Cyclotron works on the principle that a magnetic field can restrict a charged particle to move in a circular path with a frequency which is independent of its speed, whereas an electric field can accelerate it. The cyclotron consists of an evacuated chamber in which there are two Ds insulated from each other. The Ds are open along their straight edges. The chamber is placed between the poles of a very strong electromagnet. An electric oscillator establishes a high-frequency alternating voltage across the gap between the Ds. The source produces the ions to be accelerated. Suppose an ion with a positive charge Q and mass m is at the center of gap when D1 is at negative potential with respect to D2. The ion is accelerated across the gap by the electric field between the Ds towards D1. Inside a D, the magnetic field causes the ion to bend its path into a semicircle of radius r inside a D. Here, charge follow the given relation. QVB is equal to mv squared divided by r. The cyclotron frequency at which the ions circulate in the field is given by QB divided by 2 pi m. And time taken by the ion to complete a semicircle in a D is given by pi m divided by QB. At resonance condition, the ion arrives between the Ds exactly in time to be repeatedly accelerated and gains energy. This energy gain does not affect the resonance condition except increasing the orbit size. The ion describes a spiral path, gaining energy each time it passes the gap, but remaining in phase with the alternating voltage. The ion acquires the required energy to have a radius approximately that of the Ds. It is then deflected by a negatively charged plate and leaves the system. The maximum energy attained by the ion is given by product of B square, R square and Q square divided by 2m. Applications and limitations of cyclotron. It is used in the study of nuclear reactions. It is used to implant ions into solids and modify their properties. It is used to produce radioactive substances which can be used in diagnosis and treatment of ailments. At high speeds, the cyclotron frequency decreases due to realistic mass increase, causing the particles to get out of resonance with the electric oscillator. It can be used for accelerating electrically neutral particles such as neutrons. Biot-Savart law. It is a mathematical description of the magnetic field at a point that arises from a current flowing through a current element. Biot-Savart law states that the magnitude of the magnetic field dB at any point P located at position vector r with respect to the current element IDL carrying a current I is proportional to the current I, proportional to the length dl of the current element, proportional to sine theta, where theta is the angle between r and dl, and inversely proportional to the square of the distance r of the point P from the current element. Mathematical form of Biot-Savart law. In mathematical form, dB is equal to K multiplied by I and cross product of dl and r cap divided by r square, where K is the proportionality constant and its value is given by mu naught upon 4 pi. Now Biot-Savart law becomes in vector form is given by dB is equal to mu naught upon 4 pi multiplied by I and cross product of dl and r cap divided by r square. And in magnitude form, dB is equal to mu naught upon 4 pi multiplied by I dl sine theta divided by r square. Magnetic field on the axis of a circular current loop. Consider a circular loop of radius r through which current I is flowing. We have to calculate the magnetic field at a point P due to this current loop. The point P lies on the axis of the circular current loop. We consider an infinitesimally small element AB of length dl. According to Biot-Savart law, the magnetic field at P is given by mu naught upon 4 pi multiplied by I dl sine theta divided by a square. Here, theta is equal to 90 degrees and sine theta is equal to 1. Therefore, the magnetic field at P is given by mu naught upon 4 pi multiplied by I dl divided by a square. The magnetic fields at P due to different elements will be in different directions. All the components parallel to CP get added up, while those perpendicular to CP cancel out. Now the total magnetic field at P due to the whole of the current loop is given by closed integral of dB sine beta. By putting the values in this equation, we get a total magnetic field at P is equal to mu naught I upon 4 pi a square multiplied by sine beta and 2 pi r. But sine beta is equal to r upon a. Therefore, total magnetic field at P is equal to mu naught I r square divided by 2a cube. We can also write this equation as mu naught IR square divided by 2 r square plus x square within parenthesis raised to the power 3 by 2. This magnetic field acts along the axis of the circular coil. Did you know? The cyclotrons and their beam lines consume about 1.5 megawatts of power. All known magnetic fields have been found to be produced either by electric currents or by atomic magnetic moments or by time-dependent electric fields. The low-resistance shunt serves the dual purpose of increasing the range of the meter and reducing its net resistance very substantially. Summary. Let us summarize what we have learned. Oersted observed that a straight wire carrying electric current deflected a nearby magnetic compass needle. The magnetic force on a charged particle moving in a magnetic field has its maximum value when the particle moves perpendicular to the magnetic field. Fleming's left-hand rule is used for a current-carrying wire in a magnetic field, such as a wire on the armature of a motor. Maxwell's corkscrew rule states, if a screw is rotated so that it moves in the direction of flow of current, then the direction of rotation of the thumb gives the direction of magnetic lines of force. The centripetal force required by the charge to describe a circular path is provided by the magnetic force. Radius of the helix is defined as the radius of the circular component of the orbit. The cyclotron is a machine used for accelerating charged particles such as protons or ions to high energies. A magnetic field can restrict a charged particle to move in a circular path with a frequency which is independent of its speed, whereas an electric field can accelerate it.